Leaky ReLU. In the last few lectures, we learned about ReLU activation function. Here we are going to learn about something called as leaky ReLU activation function. Let us first understand why this leaky ReLU is required in the first place. Then only it makes sense to learn about leaky ReLU activation function. First of all, before ReLU, we had seen many activation functions like sigmoid, tanh activation functions. What was the main problem they had? They all had this problem called as vanishing gradient problem. Thereafter, when we learned about ReLU activation function, we saw that ReLU was able to cope up with this and it avoided the problem called as vanishing gradient. What happened with vanishing gradient? When this problem was present, gradients used to go off with time, and let us say you have a large neural network which is having a lot of layers. The early layers of this neural network, they used to stop learning. That is because gradients used to be very small, so small that you can consider them as inexistent, non-existent. So the early layers of the neural network, they used to almost stop learning. This was the problem. Thereafter, we came up with ReLU activation function. ReLU was able to solve this problem. Thereafter, we don't have a vanishing gradient problem. But what did ReLU bring in? When it took off the vanishing gradient problem, it brought a new problem into this architecture. The problem that was called as dying ReLU problem. So we had a separate lecture to detail this dying ReLU problem. Because of this problem, what happens is some neurons in your neural network, they will be dead forever. Previously, you were having vanishing gradient. Now I am saying with ReLU, there will be some neurons which are dead forever. So it's as good as not having them. This is an even more of a serious issue. Why is it? Because they will output 0 forever. So the output will be 0 for all the inputs. Gradient will be 0. So it's not just about vanishing gradient now. There is no gradient at all in order to vanish. There is nothing present, right? So this is the dying ReLU problem. Automatically, the next thing you would think is, how can you overcome this dying ReLU problem? And the answer for that is leaky ReLU activation function. So let us learn about this leaky ReLU activation function, and we'll see how this activation function is able to avoid dying ReLU problem. Okay, so this is the main part. The reason you are learning this is you want to understand how different activation functions are evolving. Okay, so you understood that ReLU evolved so that you can solve some problem, but you saw that this is having some new problem introduced. That is where leaky ReLU comes in, and this solves the problem of dying ReLU. Okay, so let us understand what is the logic that is brought in by leaky ReLU. We'll first see the idea of ReLU, and then we'll see what modification leaky ReLU is doing. So in ReLU, we had seen that f of x is equal to, there were two cases. One is it will output x as it is whenever x is greater than 0. This is normal ReLU, okay? This is about normal ReLU. And it outputs 0 whenever x is lesser than or equal to 0. Here you know that the dying ReLU problem is because of this part. That is, whenever x is negative, it used to output 0. And this is the reason dying ReLU problem used to happen. So what do you want to do now? This is the core idea of leaky ReLU, okay? Instead of making this 0, what we'll do is we'll allow a very small non-zero gradient whenever the input is negative. This is what we are going to do. So in leaky ReLU, instead of ReLU, if I have leaky ReLU, what I'm going to do is, instead of the 0, I'll write it as alpha into x. Okay, instead of writing as 0, this will be alpha into x, where alpha will be a fixed constant. And I'll fix it to a very small value. The most common value used for alpha is 0.01. Okay, this is the most common value used. According to your scenario, you may have to change this. You may have to use whichever value is most suitable. Okay. Another way of writing the same equation, the same thing, another way of writing it is, you can write it as max of x alpha x. This is also same as this particular equation. Okay, x alpha x. Whichever is larger, that is what you want to output. Next thing we want to see is how does the graph of leaky ReLU look? So this will be an interesting exercise. You already know the graph of ReLU activation function. Let us see how leaky ReLU graph will look like. Okay. So this is how the graph looks like. First I'll draw that of ReLU. Thereafter we'll see leaky ReLU. In case of positive, we know it is like this and like y equal to x line. And whenever it is negative, we had seen that in case of ReLU, it will always be 0. So it will always be here. This is how your ReLU looks like. This is your ReLU activation function. Next thing we want to see is what change leaky ReLU brought in. Okay, leaky ReLU I'll draw with red color. In case of leaky ReLU, the positive side is the same as ReLU. So I'll draw the same line. Okay. Positive side, it's the same line, y equal to x line. But on the negative side, instead of 0, I am doing 0.01 into x. So that will be a very small value, but still I'll have some value on the negative side. This is the speciality of leaky ReLU. So on the negative side, I'll be having a very small value. This is the speciality of leaky ReLU. So this delta, this is the difference that is brought in by the leaky ReLU activation function. Okay. So I'll go back to my standard color. Next thing you want to understand is what happens to the gradient now. We know the whole problem of dead ReLU or the dying ReLU problem was that gradients will be 0. So there will be no updation to be carried backward. Right? When you are doing back propagation, if the gradient is 0, you won't have the previous layers learn anything from this. This was the problem. We have to see how gradient is changing after the introduction of leaky ReLU activation function. So we'll take the gradient of f of x, that is f dash of x. Let us see how this is changing. Previously, in case of ReLU, when you take gradient of x, you got 1, that is whenever x is greater than 0. Here, in case of normal ReLU, it was 0. So the gradient of 0 was previously 0 whenever x is lesser than or equal to 0. But now with leaky ReLU activation function, instead of this, you have derivative of alpha x with respect to x. So derivative of alpha x with respect to x will be alpha. So your new derivative whenever x is lesser than or equal to 0 is alpha. So this is how you are having some derivative. I know alpha is very small, it is 0.01, but still this is better than having 0 as your gradient. So now you have a small gradient which is flowing backward. This is the advantage of leaky ReLU activation function. So what impact will this have on training? Let us say you are training some model. You have some model here. You are training this, and in each neuron, let us say you are using leaky ReLU activation function. Then what impact will it have? How will it help your training? The main point is you have a better gradient flow. This is the most important thing whenever you are training. You want your gradients to flow freely so that all the layers will be able to learn well. So this is where leaky ReLU helps you. Next thing you can say, obviously the dying neuron chance, the dying ReLU chance, that is reduced now. So because of that, you will get a faster convergence. You will be able to train faster. You will get faster convergence and a lower bias shift. Okay, what is bias shift? By bias shift, what I meant is, previously, if you got positive values, you always had very good outputs from the ReLU. But whenever it is a negative value, output always used to be 0. So there is a bias between the positive outputs and the negative outputs. This is where leaky ReLU comes in. It doesn't actually match up, but compared to this, it balances it out. So on the negative side, instead of 0, it is giving some sort of an output. So it balances out to an extent. Next thing you want to understand is How exactly should you choose the value of alpha? You may have this doubt that I am choosing some small value of this alpha here. Instead, if I choose a slightly larger value, instead of the small gradient, I may have a better gradient. That is true. So let us understand what factors impact this. Why should you not choose a very large value? What will happen if you choose an even smaller value than this? These things let us understand. So first question is, what happens if I take an even smaller value? I want to fix the value of alpha. Alpha is the hyperparameter. What happens if I choose an even smaller value than 0.01? Presently, I am saying 0.01. It need not be this, whatever be the value you want. But I am just telling you that if you choose a very small value, what happens? The problem is, then it will start behaving like a normal ReLU. Because in the normal ReLU, it is 0. In Leaky ReLU, we are doing something like 0.01. If you make it even smaller, it almost becomes a normal standard ReLU function. So this would mean the whole purpose of adding this alpha will go void. This is the problem. So this is the problem of having alpha as too small. The next question you can have is, why don't you increase the value of alpha? Presently, the negative side is not able to make any influence, but there may be many scenarios when you are training. The negative values, they may have very good significance. They may mean some things, or they may be signifying something. And in those cases, you may want to treat negative values in your training better, so that the influence of those negative values are clearly significant. This is where the question comes on, why are you not increasing the value of alpha? If I make alpha larger, then the negative values can also have a good impact on training. Then training will be better, right? No, it is not. The reason is, if you increase the value of alpha, if I have alpha and I'm increasing the value of alpha, the problem I'm going to get is even bigger. It is going to be an even bigger problem. The problem is like this. See, I'll take the same color that I use for Leaky ReLU. Previously for Leaky ReLU, I drew this here, the line. Instead of this, as I keep increasing alpha, the line will become here, here and so on. So it will come towards this side, okay? Now just think of this. What happens if you increase alpha so much that the line becomes this? If it reaches here, then the problem is, think, why did you even have this activation function? What was the main purpose? Leave about the problem of vanishing gradient or whatever. Just think, why did you even have an activation function in the first place? The whole purpose was to introduce non-linearity into your neural network. This was the whole purpose of having activation function. But what happens when you increase it to this extent? Then actually you got a completely linear line. See this is a linear line. So if you're having a linear line, then it is not going to introduce any non-linearity. So there is no purpose of having this activation function at all. It just adds a linear layer. So if you increase the value of alpha, the whole purpose of having the activation function itself will go invalid. So this is the problem. So you can't increase alpha to an extent where this particular function starts approximating a linear function. That is an even bigger problem. So what do? You don't increase the value of alpha. Instead, you always keep to try it very small. A very small value, so that you can say there is some gradient, but you always make sure that it should be far away from the linearity of this particular line. Okay, if it becomes linear, there is no point at all in having this activation function. Okay, so that is why you generally keep it as 0.01. But according to the scenario, according to the data set you have or the model you are preparing, you may have to twist it here and there. So instead of 0.01, maybe on some other problem, you may want to use 0.02. So those things you can choose. But always keep in mind, do not increase it too much so that this line becomes linear. This is the main problem. Okay. So till this point, from whatever you learned, what did you understand as the advantage of using this particular function? What are the advantages you will get if you use Leaky ReLU as your activation function? First thing is very obvious. It prevents dying neuron problem or the dying ReLU problem. Secondly, like the normal ReLU activation function, it is computationally very efficient because calculating this is very simple. Whenever you have x positive, you can simply put the value as x itself. That is very simple. Whenever x is negative, you just have to calculate alpha x, which is also very simple. So the computation is very simple. It is computationally efficient. And the next advantage you have is it avoids the vanishing gradient problem. So third advantage is no more vanishing gradient problem. This is the main use of leaky ReLU. That is, on positive inputs, now you are having the same as previously, and on negative inputs you are having some sort of a gradient, some sort of a value, so that vanishing gradient problem won't be there. And another thing you can say is that very often this generally performs better than your normal ReLU. So generally, instead of ReLU, you can go for leaky ReLU because this will perform better than your standard ReLU activation function. Let us also understand what are the problems with this. Then only we'll understand what more improvement should be done, what more activation functions are there. So in order to understand those, you should understand what are the problems with this leaky ReLU activation function. So the first problem is that the alpha or the hyperparameter that you are newly introducing, this is the next big problem. We had seen that whichever activation function we learned till now, it was introduced so as to solve some problem, but then it also ended up creating some new problem. This is what happened every time, and leaky ReLU is not any exception. It solved the problem of vanishing gradients for sure, but it came up with a new problem called as the problem with the hyperparameter alpha. What is the problem here? You are using a fixed parameter. I told you 0.01. Whichever be the value, this value is fixed. So the problem is the optimal value can depend actually on your architecture or on your data. So you may not exactly be able to find out what is the best value you want. You may have to do, let us say, a lot of tuning, or you may want to do a lot of hit and tries. Then only you will be able to understand what is the optimal value of alpha. And one more problem is, it may be the case that in your neural network, in all places, you may not need the same value. Instead, different neurons may need different values of alpha, or maybe let us say different channels will require different values of alpha. So these problems will always be there. This is the new problem that is introduced by leaky ReLU activation function. Another problem you can say on the negative inputs, it is not so consistently strong, because on the positive side it will be strong. On the negative side, the value will be very small. So many times it won't be strong enough for negative inputs. So this is what you want to basically know about it. And one more problem you can say, maybe you can say that it is unbounded outputs. In ReLU, we had seen that when x increases, the output of ReLU also increases by the same extent. So if you have very large values of x, then it is possible that the activated values will explode. The same thing can happen in case of leaky ReLU also. For positive values, if the value of x is very high, then you can have exploding activation. So these are the disadvantages of leaky ReLU. So what did we learn? We learned why is leaky ReLU required? Why is this new activation function introduced? Over ReLU, what advantages you are getting? We also learned about the new issue that is introduced by leaky ReLU. In the next lecture, we'll see what other activation we can use in order to take care of the problems introduced by leaky ReLU.